Greetings! Welcome to Electronic Circuits 1. I am Razavi, and this is lecture number 12. Today we will look at a few more examples of circuits that use diodes in them and are interesting and useful in real life. So let's take a quick look at what we talked about last time before we jump into today's lecture. Well, last time we talked about the full wave rectifier, if you remember. So here is what we discussed last time. We said that a full wave rectifier consists of 4 diodes as opposed to 1 used in the half wave rectifier. And the 4 diodes are configured as shown here, with the input applied to these 2 terminals and the output sensed between these 2. And for example, we can have a resistive load or some other type of load. Now we saw that with a resistive load we can construct the input-output characteristic of the circuit, and it looks like this. So for sufficiently positive values of the input, the output just follows the input, and for sufficiently negative values of the input, the output follows the input but with an inversion, meaning that even though the input is negative, the output is positive. So if we look at the behavior of the circuit in the time domain by applying a sinusoid at the input, we see also that the output tracks the input with a level shift. If you remember, there's a diode drop difference. There's a 2 diode drop difference between the input and output. But for the most part, it tracks the input when the input is positive, and it also tracks the input when the input is negative, but it flips the polarity by a factor of -1. So this is what we call a full wave rectifier. Then we studied a case where the full wave rectifier is used in an adapter or a charger, where we actually have a capacitor at the output, a filtering or smoothing capacitor. And we also have some resistance which models the device that we are delivering power to, for example, a laptop. And in that case, we see that the resistance discharges the capacitance periodically, and we end up with this behavior where the output goes up to the peak, but then it's discharged while the diodes are off, then it goes to the peak and discharged, and so on. So we have a ripple in this case, which is half of what we had in the half wave rectifier case. So that's one advantage of full wave rectification. All right, so today we will look at some other circuits that use diodes in them, and these circuits include the following: limiting circuits, voltage doublers, or generally voltage multipliers, and level shift circuits. So let's start with the limiting circuits and see what they are and what they mean. Well, to give you the context, remember when we talked about the Bluetooth system, we said that the transmitter sends out a waveform according to the data that we have. So here's our Circuitpedia, and you can see that the Bluetooth system takes the data, applies it to an oscillator, modulates the frequency, and then goes through a power amplifier and transmits the data. And on the receive side, we receive the data, go through a low noise amplifier, then some sort of processing, and eventually we retrieve the ones and zeros that we had sent out here. For example, from a laptop to a printer. Now the question is, if the laptop and the printer are very close to each other, so let's say they're just a foot apart, about 20 centimeters or 30 centimeters apart, then the signal that goes from the transmitter to the receiver is very strong. It has not been attenuated over a long distance. So if it is so strong, what happens to it here? What does it do to the circuitry here? It may cause problems in these circuits because the input signal is so strong. So perhaps what we could do is try to clip the signal so that its amplitude does not become too large as it propagates through this chain. So that's our objective when we look at limiting circuits. So let's go look at limiting circuits and see how they can limit the amplitude. Even though we come in with a large amplitude, we can limit it to a certain value. All right, so we are talking about limiting circuits here. And what we need to do is come up with some sort of circuit that allows us to perform this limiting using diodes. Well, let's try a circuit that we have probably come across in the past, namely this. So let's try this one first and see where it takes us. So we have a resistor R1, we have a diode D1, and we know how this circuit behaves. So this is the input, and the output is taken across the diode, so V out. Now if you remember, the input-output characteristic of the circuit looks like this. So V in and V out. We know that if the input is very negative, the diode is off. If the diode is off, there's no current through R1. The voltage drop across R1 is 0. So KVL tells us that this voltage must be equal to this voltage. So as long as the diode is off, V out simply is equal to V in. All right, so V out is equal to V in. It comes up, it goes through 0. And then at some point, when V in is sufficiently positive, the diode turns on. That happens when V in is equal to 1 diode drop. So at 1 diode drop, VD on, we turn on the diode, and from now on, the diode acts as a battery. The output voltage is exactly equal to that battery voltage. There's no change in it anymore. So we have something like this. Okay, now what does the time domain behavior look like? Well, let's go ahead and draw that. So I will change the color of my pen to red. Let's draw the output and input here. Okay, so actually let's raise this here, and I will draw a time axis, and I will draw the input waveform, V in, and now I would like to see what I get for the output. All right, well, we know that if the input goes positive beyond VD on, the output is clipped or is limited to only 1 diode drop. So when the input, if the input is small enough, the output is 0. So we are over here. But once the input exceeds a certain amount, this amount, VD on, then the diode turns on, and we begin the output. I'm sorry, okay, let me erase this to avoid any confusion. All right, so let's get out our colors correct. Here's the input, and we go to blue for the output. All right, so if the input is small, below VD on, we are over here. So the output is equal to the input. So the output just tracks it. Then the input is sufficiently positive, the diode is on, the output is just 1 diode drop. So here's 1 diode drop, and so on. Okay, now the input goes negative, the diode turns off, the input and output are equal, so we just track this, and so on. So this repeats. Now, is this what we want? Well, we said that we would like to limit the swing that we have. And we managed to limit it on this side. So even though the swing might be very large, we have only a swing equal to a peak value of 1 diode drop. So let's say 700 millivolts. That's not bad. But the problem is that the negative side is not limited. The negative side is just equal to the input swing. So can we modify the circuit to take care of this side as well? Well, yes. Maybe if we flip this diode the other way, it will clip the other side. So if we have two of these diodes, maybe we can clip the positive side and the negative side. So our limiting circuit, which sometimes we just call a limiter, is like this. We have our resistor R1, then the original diode, the D1, to clip the positive swings, and then another diode going the other way to clip the negative swings. So in this case, what we can observe is that both of these half cycles will be clipped or limited, so the output will look like this. So let me draw the input as a dashed curve. And we see that the output now looks like goes up here, 1 diode drop, then tracks, then clips at 1 diode drop, and so on. So that is V out. So that's the nice little circuit that we have, where we can easily clip it to plus minus 700, 800 millivolts, and regardless of how large the input swing is. So that's a good example of limiting circuits. All right, let's switch gears to the concept of voltage doubler. All right, before we go into the voltage doubler, I would like to show you an example of electronics in our life, which eventually actually utilizes a voltage doubler. So let's take a look and see what this example is like. An RFID tag is a little chip that we use in various applications to hold information about an item. So for example, this person wants to know the number, an item number, a serial number, anything about these various items on the shelves. So each of these items on the shelves has one chip in it, an RFID in it, and this person has something in his hand. It's like a scanner. It's an RFID reader that uses to get information about each of these items. A more familiar example is for cattle in farming. So there we also have lots of animals that we want to keep track of. They may roam around, or they may get sick, etc. So for each of these, we have an RFID attached to them. And again, using a reader, a scanner, we can determine which one is where and what condition they are in. But perhaps the simplest example of RFIDs is in passports. So now, in a passport, we actually embed a chip that holds all the information about the passport holder. Passport number, date of birth, etc. So when you go through immigration in a given country, they scan the passport and they get the information from this chip, which is much more reliable than what you see here, all the writing that's here. Right? And it's easier to see anyway, so it all appears on the screen and we can cross-check. Now, what we face in electronics in design of this RFID system is the following. We have a reader, like the reader that this person is holding, a scanner, to scan the information from that chip, right? So here's an example of a reader. You hold this reader like this, you point it at the chip, and we read the information from the chip wirelessly. All right, that's good. But the problem is that this chip is not connected to a battery. So that's what's interesting about it. It doesn't have a source of energy. Obviously, you don't want to go and charge your passport every time, so the chip cannot have a battery connected to it. So if it doesn't have a battery, then how do we make the chip work? The chip has some information in it, has some memory, some other circuitry. Obviously, it has to be powered up before it can give us any information or it can receive any information. So how do we power up the chip? So that is the interesting challenge in RFID design. So I would like to show you very generally how this RFID system works. So remember, there's a reader here that we hold in our hand and we point towards that chip. So the reader that we just saw is a transmitter. So it transmits, so here's the reader, let's draw it like a gun, and it transmits some waves, some RF waves. These RF waves propagate and are received at that chip level on the other side, in the passport, for example. Now the chip is connected to an antenna. There's a little antenna next to the chip. So here's an antenna. And now as these waves arrive at this antenna, the antenna itself now has some wave on it, some energy on it. So we take that energy, which is approximately a sinusoidal waveform, and rectify it to generate a DC. So we have a rectifier here. And maybe a capacitor. And that gives us a DC. Now you can look at that as a power supply, as a battery. So we charge this capacitor with the energy that we receive from the antenna. So this energy presumably is large enough to charge up this capacitor to some DC value. And it's this DC that powers up that RFID chip. So the RFID chip is here. And we charge it up in this system. All right, so the only problem in this case is that if we use a simple rectifier, like the things that we have seen in the past, because the signal here is not very large, this DC is not very large. So we may get something like 0.3 volts as an example. So let's say approximately 0.3 volts. And 0.3 volts does not suffice to power up this chip. This chip needs more than that, maybe 0.8, maybe 1 volt. So what's the solution? Well, this is what we will do. So we're going to change this to something else. And the rectifier is now replaced by what we call a voltage multiplier. And a voltage multiplier is more than just a rectifier. It multiplies what we could be getting here by some number. For example, if it's a voltage doubler, we double that. If it's a tripler, we triple that, etc. So the voltage the DC voltage that we get here is now maybe 0.9 volts. And that's good enough, that's high enough to drive the chip. So that connects to the chip, and the chip is able to operate. The chip now operates. It gives us the information that is stored on the chip, for example, the passport number or the date of birth. And then it actually sends the stuff back through the antenna, back to the reader. But that's not our concern at this point. So this is an interesting application of voltage multipliers, voltage doublers, triplers, etc., where we really have only this solution. We don't have any other solution, because this DC was not enough to turn on the chip. So keep that in mind, and now we go back and look at a voltage doubler. Okay, so now we study what a voltage doubler is. The voltage doubler, which uses two diodes, is probably the most difficult diode circuit to analyze. And it's difficult because it combines a nonlinear element, such as a diode, with capacitors. And if we're not comfortable with capacitors, especially in the time domain, and we're afraid of the nonlinearity of the diodes, then the result becomes very complex. So for that reason, you really have to be with me at all time. You have to be very patient with this development, maybe take a break once in a while to make sure that you follow these details and understand how the circuit works. The circuit itself doesn't look very complicated, but the operation is pretty interesting and complex. All right, because the operation is complex, we will start with some very simple observations and then actually go through the voltage doubler circuit itself. All right, so let's start with some observations. First, I would like to make you comfortable with capacitors. So we go back to Circuits 101, circuit theory, and remember how capacitors operate because we need them here. Well, in the first observation, we know that to charge a capacitor, we need to place positive charge on one plate and negative charge on the other plate. So if we have a capacitor like this and we want to charge it, if we put positive charge here, we also need to have negative charge here. These go hand in hand. We can't have a capacitor where we have positive charge on one side and no charge on the other side. All right, so that's one principle we need to remember. Okay, observation number 2. Let's take a capacitor, call it C1. We apply a voltage on this side, we call it Vin, and we leave this side open. All right, not connected to anything in the world. So that is open, and we are interested in this voltage. So the question is, if Vin is a simple step from 0 to some value, let's say 0 to 1 volt, what is Vout like? So here's Vin as a function of time. Vin jumps from 0 to 1 volt. That's Vin. And we need to plot Vout as a function of time. So let's change the color of our pen to maybe this and see what we get. Okay, so we have to do this very carefully. This is something we will need in the voltage doubler. So we have to understand this very, very clearly. This side is open, which means there is no possibility for charge to come through this wire to this plate. That plate can never receive any charge from anywhere, regardless of what we do on this side. That means that this plate cannot receive charge either, because in point number 1, I said we need positive and negative charge on both plates. We can't have one without the other. So that means that this capacitor in this situation can never be charged. And that makes sense, because if this is open, we never have any current. If we have no current, we have no charge. We have no charge, the capacitor can never be charged. So if the capacitor starts with an initial condition of 0, that initial condition will remain. So we will assume throughout this analysis that the initial condition is 0. Okay, so if the capacitor doesn't charge, it means that its voltage is always 0 if it starts with 0. So then what does V out look like? Well, KVL tells us that V out has to be equal to V in because the capacitor has no voltage on it. So V out exactly looks like V in. So V out is also like this, jumps from 0 to 1 volt. Strange but true. So again, some students have difficulty when we have an open circuit here, an open circuit there. Sometimes we have a resistor here, sometimes we have a capacitor there. But it doesn't matter, there's no current through the device, so there's no voltage on the device. Okay, let's go to point number 3 and make the circuit a little more complex. So now we have one capacitor here and another capacitor here. And again, a voltage source, V in, and we would like to find V out. Again, assuming that the initial conditions on the capacitors are 0. Okay, how do we do that? Well, there is a capacitor between the input and output, and there's a capacitor from the output to this point. This reminds me of a resistive divider, but these are capacitors, not resistors. So maybe what I should do is first replace these with a general impedance, find out how V out depends on V in, and then replace that impedance, each impedance, with this capacitor or this capacitor. So a more general version of the circuit looks like this. We have an impedance called Z1, another one called Z2, and then we have an input and we have an output. So now, in analogy with the resistive divider, we can write V out over V in. So if you go back to your circuit theory, you will remember that V out over V in is equal to Z2 over Z1 plus Z2. So far so good. Now let's go ahead and replace Z1 with a capacitor and Z2 with a capacitor. Now you have to remember what the impedance of a capacitor is, what the expression is. So I will write that here. For a capacitor, the impedance is equal to 1 over Cs, S the complex frequency. So we'll go ahead and do that now that we have found the general expression. So this will be 1 over C2S over 1 over C1S plus 1 over C2S. And that comes out to be simply C1 over C1 plus C2. So this is a fascinating result. It says that the voltage at the output of this circuit divided by the voltage at the input of the circuit follows a simple equation. This equation, in fact, is very similar to what we had for the resistive divider, with a slight change. In the resistive divider, we had this resistor divided by the sum of the two. Here, we have this capacitor divided by the sum of the two, C1, not this capacitor divided by the sum of the two. So that's the only difference we have to remember. Otherwise, we will call this a capacitive divider. Just the way for the resistive divider we use resistors, here we use capacitors. So in a sense, this is an attenuator. The output voltage is smaller than the input by this factor. Okay, so the next observation is the following. We will take a look at one circuit that consists of one capacitor and one diode for now. We're just trying to take baby steps towards that more complete voltage doubler. So here's the circuit that we want to analyze. One capacitor and one diode, C1, D1. So an input is applied on the left, and we are interested in the voltage at the output, V out. So we assume that the input is a sinusoid, and we would like to see the waveform for the output. This is a fascinating circuit. Now, because the study of the voltage doubler is already complex, we will assume, for simplicity, that the diodes are just ideal diodes, the ideal model for diodes. So to refresh your memory what the ideal diode model looked like, it was like this. We said that the diode turns on not for 700, 800 millivolts, but just for 0. So as soon as the voltage across the diode wants to become positive, we turn on the diode, it becomes a short circuit. And if the voltage is negative, it becomes an open circuit. Very simple. Open circuit, short circuit. That's it. So that helps us simplify things for now. Of course, you can always, at the end, go back and assume a constant voltage model and have a more realistic picture. But for now, we'll just stay with that. Okay, so let's assume this is an ideal diode. If it's on, it's a short circuit. If it's off, it's an open circuit. No battery in there. And let's try to plot the waveform. So I will begin with the input waveform as a sinusoid in red. So here's the input waveform as a sinusoid in red. And so that's input. And now I change the color of my pen to something else, maybe this brown for the output. Okay. All right, so we have to analyze this very carefully to make sure that we don't get confused somewhere along the line. All right, so again, assume that the initial condition on the capacitor is 0, no voltage on it. And this voltage starts going up. So what happens to this voltage? Well, three possibilities as usual. The voltage can go up, it can stay constant, or it can go down. It's unlikely that this voltage goes down, right? We don't have any mechanism for this voltage to go down. So two possibilities. This voltage can go up, or it can stay constant. Well, let's say it goes up. If this voltage goes up, this voltage goes up. All right? So because we started from 0, if this voltage goes up, it means it becomes more positive. But we know that an ideal diode does not allow anything other than 0 volt on it when it turns on. So as soon as this voltage wants to become positive, the diode turns on and becomes a short circuit. So the diode actually keeps this point at 0 volt with respect to here. If it were a constant voltage model, it would be not 0 volt, it would be 0.7 volts. But for now, for simplicity, that's what happens. So as soon as the input becomes positive, the diode turns on and we have a short circuit here. So all of this voltage drops across C1. So that's what the circuit looks like over here. We have capacitor C1, then we have a short circuit for the diode, and then we have the input voltage source. So what's interesting is that, of course, V out is 0, but the capacitor is charged as the input goes up. So as the input goes up, the right plate of capacitor is at 0, the left plate is going up, so the capacitor charges up. So we go all the way to here, and during this time, the output is 0 because the diode is a short circuit. So that's V out. The diode is a short circuit, V out is 0. All right, so then what happens? Okay, so at this point in time, we have charged the capacitor to a certain amount. How much is the voltage on the capacitor at this point? Well, let's call this V0 as usual. So what we see is that we have V0 across C1 at this point in time, if you want to call it T1. Now after T1, the input starts going down. Then what happens to this output? Right here. Three possibilities. It goes up, goes down, stays constant. Okay, so again, it's unlikely that this will go up, so we only consider two cases. Okay, can this voltage stay constant at 0 when this point wants to go down? So here, the input is going down, and we are wondering if this voltage stays constant and stays at 0. This voltage here. Okay, well, if this voltage wants to stay constant at 0, and this side is going down, it means that charge is coming out of the capacitor. You are discharging the capacitor. But for the capacitor to discharge, it needs charge to go from right to left. And that charge has to come through the diode. So some charge has to go like so. But we know that is not possible for a diode. A diode can conduct only from its anode to its cathode, not the other way around. So we cannot keep this voltage constant. That means the only possibility is for the diode to turn off. So at this point in time, as soon as the input starts going down, the diode turns off. So let's draw the circuit again over here. So in this little quarter cycle, the circuit reduces to the input and VC1 and C1 and an open circuit because the diode is gone. So V out. So now what happens? The input starts going down, the output is an open circuit. What should we expect for the output? Remember here, when the input went up, the output went up because it was open. So here, when the input goes down, the output also has to go down. The output starts going down. And in fact, it goes down by the same amount that the input goes down. Remember here, the input went up by 1 volt, the output went up by 1 volt. Same thing here. If the input goes down, the output also goes down. So the output was here, it has to go down. So the output will follow this, except that the initial values are not the same. So the output will start going down like this. So when the input has reached all the way down here to minus V0, so this is minus V0, how much is the output? Well, that's easy. We can say that the input changed from plus V0 to minus V0. So the input went down by 2 V0. The output must also go down by 2 V0. Because the output started at 0, if it goes down by 2 V0, it will end up at minus 2 V0. So here we have minus 2 V0. That's for the output. All right, so now the input goes back up, and this goes back, and so on, and we won't worry about that too much for now, but that's what we get. So the key point I wanted to convey to you is this behavior here, which is very interesting and very different from what we have seen in the past. So the capacitor was charged to V0, so that the output is 0 when the input is V0, right? And when the input starts falling, the output also starts falling to minus 2 V0. Now you can begin to see signs of what we call voltage doubling. The input has a peak swing of V0, but the output now can go to minus 2 V0. We're not there yet, but that's an interesting case. Okay. So the next question that arises is, can I design a circuit that does the opposite, meaning that the output, instead of going from 0 to minus 2 V0, goes from 0 to plus 2 V0? Can we do that? And what we are thinking is, if we flip this diode upside down, maybe that will happen. So let's go to the next page. Let's add a page here. So what we are thinking is the following. So this will be another circuit consisting of a capacitor, but the diode pointing upward. So C1, D1, and a voltage source here, V in. So the question is, in this case, what do we get for V out? Still assuming that the diode is an ideal diode. So as usual, we draw our input in red. So here's our input. That's input, and we would like to plot the output. So I will give you 90 seconds to try to plot the output. All right, so what did you get for the output waveform? Well, let's just do it step by step. Let me change the color of my pen to blue. Okay, so we begin from here. Vin is going up. If Vin is going up and the capacitor has zero initial condition on it, we don't expect the diode to turn on. If the input is going up, this wants to go up, so it's unlikely that the diode will turn on. So let's assume that the diode is off. If the diode is off, it is an open circuit. If it's an open circuit, as we saw in our second observation, if the input changes, the output changes, exactly like the input. So because the input is going up, the output will go up. It will just follow the input because there is no current through the capacitor. There's no charge flow through the capacitor. So the output just goes up all the way and comes back all the way. So far the diode has been off. The input and output are just the same. All right, now the input becomes wants to go negative. So this one wants to go down, and the question is, what happens to this point? Again, three cases. Goes up, goes down, stays constant. So which one makes sense? Well, if this point wants to stay constant at 0, then because the left plate of C1 is going down, we need to have charge flow. So for the charge to flow this way, this diode has to turn on. The diode turns on, it becomes a short circuit, keeping this voltage equal to this voltage. So over here, our circuit looks like this, just an open circuit. Whereas once we enter this half cycle, the circuit becomes like this, because the diode has become a short. The current is now flowing this way. right? The input is negative. You want to produce charge this way. The diode turns on. It becomes a short circuit. So the output is 0. The output stays 0 up to some point. Okay, so the input goes to its maximum negative number, so minus V0, and then starts taking off towards positive values. Again, the question is, what happens past this point? Do we still have a short circuit? Meaning that, is this diode keep on, or does it turn off? And again, we have to ask the same question. Does the output go up, go down, and stay constant? And what we will immediately see in analogy with the previous example is that the diode has to turn off. The diode turns off, which means the output begins to follow the input. And if the input goes up, the output goes up. If the input goes up from minus V0 to plus V0, if the input changes by 2V0, the output also has to change by 2V0. So the output goes all the way up to 2V0. Now past this point, it does other things. We don't worry about that too much. But this example is just the reverse of the previous example, right? We now can go to plus 2V0. Now if we take these ideas and try to put them together, we begin to form the actual voltage doubler circuit. So let me draw the voltage doubler circuit, and then we will analyze it. So here's the actual promised voltage doubler. The voltage doubler consists of a capacitor, C1, a diode, D1, just like this case. Then past this, we have one more diode, D2, and one more capacitor, C2. And now we have our output voltage, Vout. And the input is again a sinusoid, Vin. So this part of the circuit is familiar. This part of the circuit is sort of familiar. Remember the half-wave rectifier with only capacitive load? But now when we put them together, also some interesting things happen. So it's not as easy as saying, okay, I have this, which follows that. I have this, which follows what I know before. And I just deliver this output to this input, right? It's a little more complicated, but no problem. We'll take our time and understand what happens. Okay, so let's again plot the input and output as a function of time. So let's go change the color of the pen to red for the input. So here's the input. We'll draw it over some cycles. And so on. So that's Vin. Again, having a positive peak of plus V0 and a negative peak of minus V0. And now we change our color for the output. So you go to the output. Okay, so let's see what happens. Again, assuming ideal diode models for simplicity. Well, what we see is that when the input starts going up, not much happens here. Okay, well, let me actually start from here just to simplify things. It's a little easier if you look over here. So don't worry about this part of the waveform. Let me just erase this part of the waveform. We assume that we start from here. It's easier to analyze the circuit if you start from here. Okay, so, all right, so the input starts going negative. When the input starts going negative, if you remember what happened here, when the input goes negative, the diode turns on, keeping this voltage at 0. So let's call this node A. It means that at this point, D1 has turned on, and A is shorted to this point, right? Okay, so if you have a short circuit here, the rest of the circuit knows nothing. There's no current flow to the rest of the circuit. The rest of the circuit can stay as it is. If the initial condition on C2 is 0, V out is 0. In the meantime, because it's a short circuit, C1 begins to charge by the input, as we saw before, from here to here. So from here to here, the circuit can be redrawn as an input, C1, a short circuit here, and D2 is open, and C2 is just holding 0 on it. So we see that the output is 0 from here to here. So far so good? Okay, now what happens past this point? Past this point, the input wants to go up. So remember what happened here? As soon as the input wanted to go up, the diode D1 turned off because we couldn't have a charge go the other way. So as soon as the input wants to go up, this diode turns off and this short circuit is removed. So now here's the situation. We have 0 volt here. This diode is turning off, and this voltage is going up. So what happens at this point? This point also wants to go up. Remember, the output wants to go up. So this point, point A, wants to go up. So let's draw what the circuit looks like past this point. Well, if the circuit if the point A wants to go up, what happens to D2? D2 wants to turn on because its anode is becoming more positive than its cathode. Its anode starts at 0 and wants to go up. So D2 turns on. So over here, the circuit is as follows. We have C1 as always, our input as always. This guy turns off, D1 is no longer in the picture, and D2 becomes a short circuit because it's turned on. So we have a short circuit, and then we have C2. So the diode D2 is over here, but it is a short circuit. Okay, so do we know the circuit? Yes, it's a capacitive divider, as we remember from the previous slide. And let's say C1 and C2 are equal. For simplicity, that's usually the case anyway in the design. So that means that the attenuation factor from here to here is just 1/2. Because we have C1 over C1 plus C2, it's 1/2. That means that if this voltage changes by some amount, this voltage changes by half of that amount. Okay, so now let's get everything under control. The input voltage goes from minus V0 to plus V0 in this configuration, right? Therefore, the output goes from 0 to 1 V0. If the input changes by 2 V0, and this is an attenuator by a factor of 2, then the output has to change by 1 V0. So the output starts from here and reaches 1 V0 here. So this is the V0 line that we had before for everything. So that's V out, and it reaches 1 V0. Okay, so I repeat. In this configuration, D1 must turn off because the input is going up, just like before here. D2 must turn on because this side wants to go up. It forces D2 to turn on. Remember that the initial condition on C2 is 0. This is 0. This wants to go up above 0. D2 has to turn on. So we have a capacitive attenuator. It attenuates anything that we have here by a factor of 2. If the input goes from minus V0 to plus V0, it changes by 2 V0, the output will change by 1 V0. So the output starts from here and ends up here. All right. Now what happens if the input wants to go down? Okay, so the input wants to go down here. from its peak value. And what we observed is that because A and the output were shorted together, they are both sitting at a value of V0. So we are right at this point in time. The output is at V0. A is also at V0 because D2 is a short right here. The question is, as soon as we start going down, what happens? We have two diodes and we have to worry about both of them, right? Do they turn on, do they turn off, etc. Okay, well, let's think about D1 first. Can D1 turn on at this point in time? Well, no, because A, which is equal to V out, is at plus V0. This point is at plus V0 with respect to this point. So it's far from being able to turn on D1. To turn on D1, this voltage has to want to become negative. But we are way over here, not over here, so D1 is still off. So far so good. How about D2? This voltage wants to go down. Now the question is, does D2 turn off or does it not turn off? Well, same question as before. Does this voltage remain constant? Does it go up? Does it go down? And if you follow that methodology, you will quickly see that D2 has to turn off. So when D2 turns off, in this regime, the circuit reduces to one voltage source, one capacitor C1, and D1 is off, D2 is off, so we have C2 only. That's C2. Sorry, let me draw this elsewhere because I will need the space for my waveforms. So let me draw that a little lower. Okay, so in this regime here, the circuit reduces to a voltage source, C1, D1 is open, nothing there, D2 is open, nothing there, and then C2. So how much is the output voltage in this regime? Well, even though the input is changing, there's an open circuit between C1 and C2. So C2 has a constant voltage on it. And that voltage is known. That is the peak voltage that we had at the output, right? Right here. So from here on, the voltage on the capacitor does not change. It's constant and is equal to V0. So the output voltage remains constant. All right. Okay, it remains constant up to only here. So again, let me make a quick correction. All right, so V out is constant, equal to V0. In the meantime, the input goes down. The input goes down, reaches here. When it reaches here, what should happen? D1 turns on. Just like before. Remember here D1 turned on? So we go down, and then when we come back up, we turn on D2 again. And what we see is that from here on, if I go back to my pen, this charges again, but it charges up by a smaller amount. So this time, this goes up by V0 over 2. So I will leave this as an exercise for you to follow the waveform past this point and see exactly what happens. But the result is that in the next cycle, the voltage on C2 increments by only V0 over 2, not by V0. And if you follow this for more cycles, you see that then it increments by V0 over 4, and so on. So the final value of the output voltage, the voltage across the capacitor, will be V0 plus V0 over 2 plus V0 over 4 plus V0 over 8, etc. And if you expand that, of course, we know that's equal to 2V0. So eventually, if you wait over some cycles, this approximately becomes equal to 2V0. And then it stays constant. So, or asymptotically approaches to V0, and it's just approximately equal to 2V0 forever. So what's interesting in this circuit is that the input is a sinusoid, is AC, but the output, after we wait some cycles, if you wait 5, 6, 10 cycles, then you quickly reach there. After some cycles, becomes a constant value. It's a DC value. And that DC value is useful to emulate a battery, as we saw in the RFID example. And it is possible by means of 2 diodes and 2 capacitors. The capacitors are usually equal. The diodes are also identical. All right, so the purpose of this was to show you how we can generate twice the voltage, the peak voltage at the output, and keep it constant as a function of time so that it can look like a battery for a while. All right, that's the voltage doubler. Let me briefly talk about the level shift circuit, and then we conclude this lecture. So level shift, this is actually very simple. So we spend 1 or 2 minutes on it. Level shift simply means this. Sometimes we have a signal in our circuits. So here's a signal as a function of time. And we would like to shift this signal up or down for various reasons. So for example, I would like to have a signal, let's get the colors here. So I would like to have a signal that looks like this. It's shifted down by some amount. So it's always lower than the input signal. So now if this level shift, if the difference between these two is on the order of 1 diode drop, then that's pretty easy to do. We take the input signal, apply to a diode. V in and V out. If the diode is guaranteed to stay on, then it looks like a battery. So the input voltage is always higher than the output voltage by 700, 800 millivolts. Or the output voltage is less than the input voltage. So as the input voltage goes up and down, the output voltage has to go up and down because they're connected by a battery. But there's a level shift of 1 diode drop. The only thing is, how do we guarantee that the diode is on? So to guarantee that, we pass a constant current source through it. So we call this I1. It's an ideal current source, and it guarantees that this diode always has a current through it. If it always has a current through it, then it must be on. And if it's always on, then it has a certain voltage, VD on, and that gives us a level shift. As an exercise, now you can ask yourself, how can I shift the signal upward instead of downward? So you can imagine that this diode has to be flipped the other way, the current has to come the other way to bias it up, etc., but that's relatively straightforward. All right, this was our tour of diode circuits. We saw many different examples, and we have a pretty good understanding of various types of circuits that incorporate diodes. From next lecture, we will begin to look at circuits that use transistors in them. And suddenly they become even more interesting than the circuits that have only diodes in them. I will see you next time.